Okay, and a very good morning. I think we are live with a stream, another stream, where I'm looking at learning the Rust programming language, trying to battle its infamous learning curve. And in the process of that, I'm trying to write some interesting software. What I've done in the first part of this series was to write a small epidemiological simulation. And what I thought I would do today was show some very interesting benchmarks. Because I rewrote the same software in Python just to see to get a sense of the speed difference between these two versions, and the results are striking. And so what I want to do today is I'm just going to go through the source code of these two versions side by side. I think it's an interesting comparison to see like how these two languages similarly and also differently resolve issues and just get some ideas for maybe how to optimize the Python version if needed. But the more interesting part today, and that's more relevant to the learning curve, is that I want to try to make the Rust version of the simulation multi-threaded, so that hopefully we can utilize the resources of modern computers better, because right now both of these versions, both the Rust and the Python version, are single core or running on a single core. So I think we'll just go straight to it. The first thing, just to recap for those that haven't been part of this stream before, the output of the software that I've written, or the software that I have written, simulates the course of an epidemic. And we've simulated a certain number of people that infect each other and then build up immunity as they go through the course of the disease. Everyone recovers from the infection. So what we can see here on the x-axis is number of days that we have simulated. So in this case, we simulated 10,000 people for 100 days. And what is interesting is that you can see as the days progress, you will see that the number of cases initially grows very slowly, and that is this exponential growth effect that we see in the current COVID epidemic. And you can see that this model simulates that pretty well. Then it sort of grows faster and faster, and at a certain point here, enough of the population in this simulation has immunity towards the condition, and it then starts to taper off and eventually levels. There is a lucky few people on the top here, in which case they are at the point where they're lucky enough to not get infected for a long time. So no one is in this simulation. It's random who gets the infection, in the sense that every sick person will infect 3 more people. And in this case, it's completely random who those people are. So in this very simple, this is a simplified model. And so it does not take into account things like people living in households together or clusters geographically. It just simulates this simple pattern of spread. So by randomly picking someone, it means that if you're fortunate enough, a small number of people here, I guess maybe it's like 500, are lucky enough that they will never get the condition. And the reason for that is, of course, that as immunity builds up in the population, the chance of successful infection of another individual drops. And some people are just fortunate enough that they will never get into that situation where they get infected. The other interesting graph is this curve here that shows the number of active infections as the simulation progresses. And of course, these two mirror each other very closely, because it is the same data, it's just 2 different views. So again, this is a very simplified epidemiological model, but the interesting part was not so much the model itself as the writing of the model in Rust. So what I decided to do was I wanted to know, if you build a model like this, it does executing a simulation like this takes a bit of time. And one of the arguments why you might want to do something like this in a language that is not dynamic like Python or basically the reason you don't want to do this in an interpreted language is that you would expect to get some speed benefit from a compiled language. And Rust is famous for being pretty fast, right? So I did to check what kind of speed gains we would have, I did something that I thought at least was very interesting. So I wrote a Python version of the simulation, and then I compiled the software that the Rust version of the software into an executable, and I used the release flag here on the compiler, which means that it should apply optimizations to the software. So here's a question, if anyone is wondering: how much faster do you think Rust will be? Do you think Rust will be slower? What do you think is the speed difference? So what we're going to do is we're simply going to time epimodel, and epimodel is just that software. We'll go through the code in a moment and compare the Python versus Rust version, because of course it's not all about speed, it's also about development speed and how much you can change your code, and whether you know what you're going to do, or if you're prototyping and just trying things and so on. Let's run the model, and in the settings that we have in this compiled version, it's hard coded in, is I think it's 100,000 people for 300 days. Let's go. Actually, what we can do is we can open the system's resources, system monitor. We'll put it over here. Then we can put the let's see, we can put our version there. We're also going to compare with the Rust version in a second, or the Python version in a second. Okay, so let's time epimodel. Let's just see what it goes. But actually, what we can do is we can try this later with a little bit more people as well. Let's try it. That was incredibly fast. It was so fast it didn't even get picked up over here. Or maybe it simply didn't use that much resources at all. So the process of simulating 100,000 people for 300 days took 0.2 seconds in Rust. Now we will do the same thing here in Python. And of course, there's a build when you start Python. There's probably going to be sort of a ramp on. It's going to take a little bit to boot up the Python system itself, if that you can say it like that, or it will import the modules and it will do a lot of different things to get that going. So if the number of people in the simulation is very small, then you would expect that startup time has some effect. But when you have a simulation, so in this case here, we think that if the simulation really is this fast, then the startup time would matter more. But let's try it. Okay, CPU history really high. One core is up to 100%. You can clearly see it's not multi-threaded. It's still going. The memory is not so high though. And it took 16 seconds to do the same thing. So these numbers are of course just staggeringly different. So either I am doing something wrong, or this is actually what you are sort of expecting to get. I try to optimize a little bit the Python version. We'll have a look at it in a moment. But one thing we can do is we can try to increase. I think the Rust version executed so fast that you hardly noticed anything in this systems in the view here. But what we can do is we can go and we can change. We're gonna have a look at these two later. But in the Rust version, let's dial it up to 1 million people. We'll do the same in the Python version. So it's 000, and then it's 000 here. I should probably use scientific notation there, because I've saved the Python version, but now I have to recompile the Rust version. Do that. Got some warnings, and compiled in a release optimized version in 1.26 seconds. Okay, let's try it now with 100,000 people. See if we get a little bit more. Now it's taking more. Yeah, you can clearly see the. Okay, so it did 100,000 people. No, it did 1 million people, sorry, in 4 seconds, 4.2 seconds. And it did put a dent in the memory, but there's a very, very rapid execution here. And again, you can see this executed on a single core. Okay, next step. Okay, so we did. So the first version of this, okay, so 100,000 people took 16 seconds in Python. It took 0.2 seconds in Rust. 1 million people took 4 seconds in Rust. And let's try it here in Python. It's core number 3 this time, being responsible for the execution. Okay, so how much longer did it take? It took roughly 4 times. Oh, yeah, it's much longer actually. If these two grow linearly with each other, then we would expect a much longer here, or it could have one of these execution times that you cannot calculate that way. I don't know this notation for that, but it's the big O notation, isn't it? Let's give it a moment. So one interesting thing that we have discussed briefly in the streams before is that perhaps when you are simulating a large number, or perhaps the size of the population that you need to simulate is not really, oh, interesting. Oh, that was super interesting. It now switched cores. Why did it do that? How did that happen? So that is a mystery to me. Does that mean that it's doing something else now? Because initially, why would it do that? We'll go through the code in a moment and we'll see if this sort of makes sense now. And now it switched back again. Why does, because that is something that I was completely not expecting. Why would it do that? Why would it ambulate between the cores? It's running in a virtual machine, but I can't really see that affecting anything here. Okay, so what I was saying was that it's when you make a simulation like this, I don't know if there are sort of rules or how many. It's like a statistical thing. You need a certain statistical power to show a difference between some things, and how many people do you need to simulate for the numbers here to be, for the numbers that come out of here to be relevant and translatable. It might be that in this simulation you don't need to simulate more than 100,000 people, and if that is the case, then perhaps it doesn't matter at all if you wrote this in Python or Rust, right? Because you would get the same results in Python. So that's also a good argument to review the difference between the codes. Could it be that when it switches CPU, it's because it changed the task that it was doing? So first it will allocate 1 million people in an array, but how long can that realistically take? Because it says here that it created the simulation very fast. Then what it's doing now is that it's looping through and it's infecting more and more people, meaning that every infected person will infect 3 people over time. Okay. Yeah, so we did actually not manage to write the output here, but that is okay. Yeah, actually did the same problem here as well. Yeah. But I don't think this is the this is just a bug that prevents writing of the output. I don't think it's the thing that slows this down. Okay, so it took 3 minutes to execute this 1 million person simulation. So yeah, that is a significant difference. So again, the mechanism of this simulation is that it has a large list of people, a large person objects. Those people have when they get sick, when they get infected, they develop a clinical course. And during that clinical course, they have 3 days where they don't infect someone, then they infect someone, that's a random individual, and then that repeats 3 times, and the final day is a recovery, which is what happens at the end, or the state of the person. So the system will only look at the people that are infected. This means that the load that the system has to work with increases as more and more people get infected in the simulation. But in any event, what we ended up with, so what it does also as it ticks through the days, it takes those infected people and it pops the first element in the sick day, in the clinical course. It takes the first element that's in that list and pops that out. So it's sort of the vector that contains the states of the individual as it goes through the sick days gets shorter and shorter. Eventually there is only one element left in that vector, and then the person is no longer infected. The person is no longer susceptible, and the person goes out of the simulation. So could of course be that there is something about the vector manipulation in Python, or yeah. Okay, but the differences that we've seen here are striking, right? So you can compare these two execution times, and it didn't feel like this was linear. It felt like as we added more people to the simulation here, we added a lot more explosively slower here. So you could probably optimize these things. I'm sure there is techniques for that. But in this simple example, the just unoptimized doing something with a large list of a large vector, it's striking the difference between Python and Rust, right? How is it even possible the difference to be so big? So let's jump into the source code and have a little look, because okay, so let's say that this speed gain is real and that I haven't made any mistakes comparing the Python and the Rust version. Let's say that these two are roughly equally good and that I didn't surprisingly stumble upon a perfectly optimized Rust version during my learning curve, or that I didn't like make any huge mistakes in the way the Python version works. Then just this out of the box performance gain is crazy. Of course, this is a particular situation because it involves a really, really large list that you're repeatedly looping and filtering on. But still, it is intriguing to see this difference. Because I would assume that this difference somewhat translates into code you just randomly write, right? If you don't write code that is optimized, if the default setting or the default effect of having this language, one language over the other, is this kind of speed increase, you're onto something. But there's more to this, and I thought it would be interesting to compare, like, what does the source code look like between these two versions? Because we have now the same program written in Python and in Rust. So I thought we would just compare directly what the various parts of the software looks like as they are written in these languages, because it is a very, very interesting to think about. Okay, so one of the benefits of Python is, of course, that first of all, or the perceived benefits of Python is that it doesn't have this type system that checks during compilation or preparing of the code. It is an interpreted language without type checks, right? So it has weak typing. Well, Rust is absolutely strongly typed. It has a really powerful type system. So writing these two versions of the software, that was an interesting experience, because of course I spent 5 hours writing the Rust version. Much of that, or I spent much more considering the research that I did to learn the various things. But part of the reason I had that is, of course, my learning curve, right? I'm learning this language, so it took me a while to get to the point where I could write it. But then I wrote the epidemiological simulation in Python, which is almost the same code line for line, and I wrote it in 45 minutes. I know Python from before, although I still had to look a few things up because it has been maybe a year and a half since I touched Python last. But one thing that was so striking writing these versions, and this is intriguing, is that when I wrote the Python code, I had to run it to see if it failed, right? So this sort of the feeling of these two programming styles was that I now had to write it to test it. While in Rust, I felt more like, okay, so if it does compile, I just felt more sure that it was going to work. It might not necessarily do what I wanted it to, but I could be sort of sure that it wouldn't crash, right? And I heard people talk about this, but doing these two versions side by side really took that home. This sense that yes, when I wrote this in Rust, I felt like, okay, it's going to run now. It might have logic errors and indexes might be out of bound and whatever, but it's not going to fail for silly reasons. While in Python, it had that sense that the compilation was executing the software. Maybe that has merit, right? You could say to do test-driven development, and then you get a better that sort of works for you. But it really. I do like strong typing, so for me it felt much better to write it in Rust, even though it took significantly longer. Okay, so let's walk through the code step by step. So of course the main function is the entry point. In the Rust version we put that in a separate file and then we import the simulation. In Python I just put this in the if name main clause, and these two things do more or less the same thing. So one thing that is certainly the case Actually, we can remove, let's remove 900,000 people from the simulation in both these, in case we do want to run it again. So I think it is absolutely clear that Python is less verbose. Sim equals simulation, and of course in Python you could even have name parameters, so you can do like this, and this is a exceedingly expressive way to put it, right? While the Rust version is you have to create a mutable variable sim, and then you have to use the constructor function. And of course, Rust doesn't have constructors, but it has static. Also, it has functions that are encapsulated in the type's namespace. So effectively, what you end up with here is a factory function for creating simulations. It doesn't have name parameters, I think, so I can't do this. But I have to say, for the first line of code, it really fires off well for Python. Just the formatting of in this case, we want to tell how many people are in the simulation. We're just dropping that out. I think there's no real difference between these two. They're in fact very similar. Rust uses a macro for string formatting, but they are similar. I think perhaps even the Rust one is a little simpler. Okay, so yeah, so we create. So we want to see the 10 infected people. So we have to loop from 1 to 10 and infect random people. They are also very similar. I don't really see any big difference between these versions. We pick a random index from the simulation, then we infect that one. We do exactly the same here. We pick a random index from the simulation and infect it. So they are very similar. And then the same is true for the days that you loop through. We do 300 days of simulation. So we go from 0 to 300, and then we just say what day it is into the sim. We do the same thing here. To be honest, I actually, coming from C#, coming from C originally many years ago, I do prefer to have brackets. I never sort of started liking. I think maybe because I started programming young and I got used to these brackets, it's like my brain sort of automatically sees that these things are between the brackets, so that's a thing. Well, indentation, for whatever reason, seemed less clear to me, but this is just flame. It's nothing. It's nothing of importance. Okay, so that's the main function, and I gotta say, I don't think the Rust version has anything negative compared to the Python version. For this simple setup that we are doing here, for this simple code, they are so similar. And if you just compare these two and knew that this one ran like 10 times faster, more, 100 times faster? Well, maybe 80 times faster, then of course I would pick this one any day. Okay, so in Rust we put the simulation into a separate module. In Python, I put everything in one file except the sick day definitions. We'll get a look at that later, and that's to sort of emulate a little bit what Rust is doing. Okay. So in Rust okay, so let's just look at the object declarations. So actually we're not using this dead version, but we can leave it in for now. Okay, so here we are saying what state an individual can be in at any given time. It can be susceptible, infected, recovered, or dead, but we're not actually using this. I think we could get away with doing that. So we are creating an enum. You can do the same in Python. These are also very similar. We had to add a line here to be to be able to compare enums in Rust. We had to add this partial equal thing to get if you want to compare to one of these states to the state field of an individual. So here's a super fascinating construction in Rust, of course, is this that it has enums with data in it. So when a person is sick, you have the clinical course. Actually, let's have a look at the person first. So person here in Python, of course, you construct the object in the constructor in Python. So the class person takes an ID, and then it sets itself as state susceptible. It can be infected, and then the clinical course is an empty vector. The person object in Rust has to be declared differently, and you need to also have a constructor function. So in Rust, it's different. So this individual is then, of course, it has an ID. You have to specify the types, strongly typed, status, and the state. The clinical course is also a vector of sick day objects. So here, of course, in Python, we are creating this empty vector here as we are defining the object. This you cannot do in Rust. You have to create this vector when you instance the person object. But beyond that, I think this is cleaner and more. It expresses more what you are doing. So than the Python version. This double underscore anything never caught on with me. Of course, you're not actually, you are declaring here. You can also use type hints in Python now, so you could add type hints here to add strong typing. But of course, the nature of Python is that it is duck typing, so doesn't require these fields. It is simple. It's written simple, and if you were just making a simulation for the first time and you're just trying things out in code, then of course this would probably be faster and easier to write. Although this is more structured. The benefit of this is, of course, also you can refactor this very, very easily, right? And you can get error checking, and maybe that's also good when you're prototyping. So yeah, okay, anyway. So the other thing that we have an enum called sick day, and what that means is that as the person progresses through the disease, after they have been infected, they have like 12 days, 13 days where they are sick, and any one of those days corresponds to one of these enums. So either nothing happens that day, they are just sick, either they infect someone and then it will carry the ID of the one that they are infected inside the enum. I just love this. And the final thing is the conclusion, which is what happens when on your final day, and either you recover or you die. But in this case, everyone recovers. But it has a state, again, the same way that the infects carries the ID of the one that you do infect. The conclusion carries the state of the individual at the end of the course. This is a little bit. This is different in Python because you can't have these enums, but you can add heterogeneous lists, right? So this list of clinical course can contain anything. So I put these states in a separate module, and I said that you have these three objects that you can have. You either have a none, an infect, or a conclusion class or object. And then I added some data on these or some fields to these classes so that we could also encapsulate the ID of the one you infect when you infect someone, and the final state of the individual as they come to the final day of their clinical course of the disease. This is how I solved this. I added a date type here to try to optimize, and I'll explain in a moment why that is there. Okay, let's continue to this. So the simulation, when we initialize the simulation, Yankee scrolling here. What's going on? That's funny. Visual Studio Code is acting up a little bit. Okay, so how do we create a simulation? Well, in Rust, we create a mutable array of people. We populate it with people. So we just basically push a new person object into this array n number of times. So this code is incredibly much cleaner, or is incredibly clean in Python compared to this. This entire block here is replaced by this initialization for the structure in Python. So we create an output array. Actually, this is to keep the results, and then for 0 to n, which is n is the number of people in the simulation, we append a person. So what you can see here is that because when we create person in Python, we are creating the person in the constructor, and then everything gets so much, you have much less code, right? So we're just very, very simply appending people, and then we don't have to return. This is actually a constructor, so Python knows that what comes out of this is set ready-made simulation object. But in our friend Rust, we have to return a simulation object because there are no constructors. This is one of potentially many factory functions. I don't mind this. I actually think this is a neat way to do it, allowing you to have multiple constructors. But then again, of course, this is a lot more code. That said, because of the fact that the Rust tooling is so good, because of the strong typing, then you will see that if you have just created a new simulation object here, CLI and other IDEs will give you a lot of tooling that will simplify writing it, so it will say fill missing fields, and it will just populate this structure, so you'll basically get this without having to type it. But of course, this is more verbose. The function to pick a random individual from the simulation is similar. There's no real difference between these. The biggest difference, perhaps, if to that extent that there is any, is that you have to cast these values to other types of values, because random returns, in this case, a float. And as you multiply a float by the amount of people in the simulation, then you have to return it as an ID. In Python, there's actually a choose function that picks one individual from this list. It might actually be that there is one here in or a trait in Rust. You can do that too. But for this calculation, they are similar, except there is more type parameters here. Perhaps if you were new to programming, you would find these type parameters and the casting to be a challenge. But it is the nature of strongly typed languages that you got to do these things. Okay, let's move on to the. We can move on to the infect function, which is down here. Okay, so this one is quite different between Rust and Python. Let's start with the Python version. The infect function takes the ID of the individual we want to, or the index of the individual we want to infect. So in this case, we just pick that person out of the list. We check if the person is susceptible. Note we keep this variable. Keep that in mind, because what happens next is a little bit intriguing, and it shows the difference, right, between these languages. Then we create an empty clinical course, and then 3 times we insert this array of statuses that happen. So there is 3 sick days where nothing happens, and then there is a sick day where it infects an individual. That means we have to call this function to pick a random person from the simulation to construct this final sick day where the individual infects another one. On the final day, we say that we append a sick day with a conclusion, and that is status state recovered, so the individual recovers from the disease. And then we set on the person, we set the clinical course to course, and then we state that we put the person's state to infected. Not so easy in Rust, because you cannot have mutable and immutable borrows at the same time. So here comes complications. So complication number 1, we pick a person out of the simulation, and to do that, we have to call the get function on the people array of self. We're now inside the simulation object. We don't do error checking, so we do unwrap. This will panic if there's an error, such as if the ID is out of bounds, for instance, then this will panic with the unwrap, but you could choose here to handle the result. The error handling in Rust is beautiful this way, and yeah, it's just really nice. Then we check if the person is susceptible, so we will match the person's status. So we'll say if it's susceptible, we don't do anything. If the person is not susceptible, or it has any other state that it's currently infected, or it has recovered, so it is immune, then we return here and we don't do anything. This is, of course, also why you see a dropping number of people here, right? More and more people end up in the category where infections don't actually do anything, and then the number of new infections per day drops. So this is where it happens. So here's the so this is how we had trouble with this during the stream, is that now we need to make the course the same way we are doing here. So in this segment here corresponds to this segment here. So what we do is we create a mutable vector of sick days called course. We use this thing here, so that is this simple line here. Of course, is you gotta type out this thing to do the same as that. So there's a clear difference between these languages here. Then the for expression is very, very similar. We pick a random individual, and then we append this vector. These are also very, very similar. And then finally we push instead of append one last in the status, and then we are done. So one thing we had to do is that now we have to redefine person down here. If we keep this person, we cannot call this function here. Here came the memory management of Rust in, because this person is borrowed as unmutable here. So what happens is that we use our self to borrow this person. So this person is sort of behind this borrow of self into this function. Yeah, right? So we cannot do this as long as the person object exists. So if we just used person down here, so we didn't get it back again, then we would not be allowed to call this one, because that means that we are passing this self object also into the pick random here, while this is dependent on it. So we would not be allowed to do that. So what happens actually here is, because we redefine person down here, this person will go out of scope after this match because it's not used, and then we are allowed to do this. So this memory management thing, of course, adds a little bit of trickiness to, not just a little bit, it adds complexity to the coding. And then we have to get the person again down here. This time we get it as a mutable reference, and then we set the course and the infection. So you didn't have to think about this in Python. And this is perhaps the biggest difference between these languages, because beyond the typing and the type system, because this took a while to figure out when we were doing this on the stream. But beyond that, I have to say I don't necessarily think that this is so much less expressive. It is a bit shorter here, but I find them remarkably similar. Okay, last thing we're gonna look through then is the next day function. So what does next day do? Well, it takes the simulation one day forward, which means that it finds all the infected people. It takes the sick day that they are currently on, which is it doesn't count those days. It just takes one sick day off the array of the clinical course, and it looks at what that was. So the first thing we got to do is find the infected people. So in Python, we can use list comprehensions. So here's next day, and we want to find the infected people. So we take this simple, beautiful Python construction, which is p for p in sim people, if the person's state equals state infected. So yeah, this is gorgeous, right? You gotta love Python for this construction here. So simple, and then this becomes an array of individuals that are or a list of individuals that are infected. It's a little bit more tricky in Rust. The fact that I had to resize this window probably shows that. So we're also going to keep a list here, yeah, of new infections that we did not have to do here. I will have a look at why that is. Okay, so in our friend Rust, we could actually have taken this out and could put it on a separate line like we did here. But this is analogous to the same expression that we had over here. So this looks much more complicated, right? So we pass a mutable version of self dot people, and we get a mutable iterator. That means that we get an iterator to that's the object that helps us loop through the list, and then we apply a filter function to the iterator, which says that for each element in the iterator, we ask for the status being infected, right? In order to do this, by the way, in order to compare these enums, we had to add this this derive partially equal or whatever that is to do that. So this is not ugly in some ways. I like the way this works, and part of the interesting thing here is, of course, this is an iterator that is being returned. So when you put filter here, you are returning an iterator. So I'm not sure what happens in Python. Like, is this object here, is that an iterator based on this list comprehension, or is it actually a new list of infected people? A new array in memory? I don't know. If this is the case, then this would be slower, I assume, than having an iterator that would just happen more lazily as you loop through it. We next we take for each person, yeah, that we get out of here, we remove the first element in the clinical course. So again, the clinical course gets 1 day shorter every time until the final day. That will be the current day, and then we check what is the current day. Is it does nothing happen? Well, then nothing happens. If the person infects another one, then now we keep a list of the people we are going to infect. We have to do it like this in Rust. And then finally, if the conclusion is, if we are on the final day, then the conclusion of the final sick day includes the conclusion, so that could be either recovery or the individual dying. But in this case, everyone recovers, so we know everyone recovers. But we take the what's wrapped inside this conclusion and we put it inside. We put it as a person's current status, and that means that on the next day we will not include this person in the loop because the person has recovered, or the person has recovered. Okay, so what do we do in Python here? We do exactly the same thing. But now this is of course a much simpler construction. We say for person infected today, this is the same as current day. We pop the 0th element. So remove removes one element. Okay, maybe am I doing something wrong here? That is interesting. Should this be remove 0? If it is the case, here we have actually potentially a bug, right? If it is the case that I've been removing the elements twice as fast in the Rust version, then the speed would probably, the simulation would progress faster. Perhaps we have accidentally optimized this by making it incorrect. Before we continue the iteration through the code, let's have a look and see if this changes the execution speed of the model. So this is the current version of because now it simulates one, of course. I had already done it so that it would simulate a million. So we have changed, so we're going to put this back to the way it was. I'm just going to check this now. Interesting, this is a code review. So the first thing we're going to do is we're going to compile it again because we made this model for 100,000 people. Okay, so 100,000 people, it now seemed to conclude in 0.2 seconds. So what happens now if we alter the this to be element 0? So the reason I put 1 there, I believe, is quite simply because, does this remove? Let's actually check what it does, because it could be that I was more clever than I thought. So we put Rust vector remove. Because maybe it makes sense. Let's see. Yeah, it says remove 1. So retains. Here we go. Removes and returns element at position index. Yeah, so I do give it an index. Yep, so I actually think this was a bug in my code. Okay, so let's compile it again now, and probably we should see something like twice the execution speed. Well, okay, let's see if that holds. Let's try. No, okay, so the speed did go up slightly. At least the program is now correct. It should be more correct now than it was a moment ago. Okay, so that was a bug. So here's an interesting thing. Why would I write 1 there when, of course, as a programmer, I know that index 0 is the first element? Well, I think this is because I've been programming MATLAB for work for several years now. And in MATLAB, the first element's index is 1. So this is probably the reason why I sort of intuitively picked this one out by accident. Okay, let's continue this. Okay, so we have corrected a mistake. I think the mistake was not present in, no, we pop element 0 here, yeah. So, okay, so let's get back to it. So this match expression here, I put like this in Python. So initially when I wrote this, today can be any one of these sick day objects, right? So what I initially did is that I asked that today, and then I did is instance of, and then I said sickday.infect, sickday.none, and so on. Because I thought that maybe that involves, because I thought that could involve an element of reflection in the language, and that perhaps the reflection would be slower. I figured that it would probably be better in Python to add this sort of field to the object, where you could simply compare a number and see if what type it was. So in this case, that's why I did it like this. It did not seem to have any speed effect on the simulation. So I have a feeling that just comparing today with is instance of to these different types of sick day that you could have seem not to be any slower than this method. The match expressions are nice. I prefer the match syntax, to be honest, to these if else if things and switches and so on. The match things are lovely, and you can put expressions in here as well. So I think on that particular note, I do think that that our friend Rust wins. Okay, so because we are passing a mutable version of self into the iterator in Rust, we have to keep a list of the new infections that we will then deal with, because we cannot call self-infect from inside the iterator enclosure. So this is a Rust-specific problem, and that's why we loop through the new infections list here at the end and infect people sequentially after we've caught them up here. The final thing we want to do, and this is also an interesting difference between the languages, is that we want to count the number of susceptible, infected, and recovered people in our simulation. So in Rust we wrote a function to do that, which is actually quite nice. It takes the people array, it gets an iterator from that, and it filters it the same way we did up to find the infected people right up here. And then it just counts how many elements are in that iterator. So this is actually the same thing that we are doing here in Python. We put the susceptible, for instance, equals the length of this list comprehension that you have here. I gotta say the Python version is tidier. I did enjoy that, but it is also very expressionate and powerful what you are doing over here. So I think they're pretty equal here, yeah. And that is all our simulation does, apart from writing the CSV file as the output. So it is it's very fascinating to see these two. I have to say Rust is not lacking in its expression, or it feels of course more convoluted and complex. And because of the memory management, we ended up having a couple of situations here where we had to think differently about how we did it, and it mainly affected the sequencing of things. What you had to do certain things first so that you would have secure access to the same memory afterwards. Then you had to do it in steps and keep temporary variables to perform the next step, such as here, where we, instead of directly infecting people from within the for loop, like in Python, when you want to infect someone, it's very, very simple. You can just call self-infect on that object. While in Rust, we had to keep that list of new infections and then loop through that list a second time. But it certainly has not slowed down the language when we look at the execution speed difference, right? And step for step, these two things do very similar things, right? It could be that maybe list comprehensions is slower, and that is one of the reasons we are experiencing this dramatically slower version of the simulation in Python. Maybe there are elements in here that are slower, and we could probably profile that out. But these things are equally expressive, right? So if you wrote the Python one, you would have less trouble writing it, but the code is not necessarily less clear, I think, in Rust once you know the syntax. So yeah, and you could refactor the Rust code afterwards. If your application has performance critical elements like potentially this simulation has, then I think it seems pretty clear to me that Rust would be a very, very good alternative to Python for this particular scenario, at least. Okay, good stuff. So we have made our simulation, and we know that it works, and we have timed it, and we have found some intriguing speed differences between these versions. So again, the Python version executed in a couple of minutes, or 400,000 people, it executes much faster. It executes in roughly, was it 14 seconds? But I mean, the speed difference is so dramatic for if the Rust performs the same operation in less than 0.3 seconds. So it's crazy, the speed difference here. And I cannot, even on the re-review that we had here, I couldn't immediately see any obvious reasons why the Python version would be slower. Okay, so I think what we're going to do next is we're going to try to make the Rust version even faster. Right. So what we saw when we monitored the performance while we executed the simulation was, of course, that there's only one core being utilized. Python had that fascinating switching behavior where it switched between what core was being used. I have no idea why that is. While the Rust version stayed on one core and was so fast that it was hard to sort of see the increase in capacity. So I'm going to take just a very quick break to get myself something to drink, and then I will be back and we'll try to see if we can get this speed in Rust even lower by doing multi-threading. So that we have to think a little bit about it when we get back, but we'll think about what parts of the simulation we can multi-thread, and then we will, or how we would want to do that, and what's possible in this simulation, because it has a scenario that makes, I think, some of it a little bit harder to multi-thread. Okay, so I'm going to take just a 5-minute break, and then I will be back. Let's put up a nice little banner here. So this is a thank you thing, but we don't want to do that. We want to say be right. So back in 5 minutes. Back in less than 5 minutes. There we go. Oh, there we go. Okay, so I'll be back in a moment, and so stay tuned if you're watching. Okay, hello everyone, I am back. So in this stream so far, we have run a benchmark Python versus Rust by running the same code, more or less, in both languages, and we find still a dramatic increase in speed with Rust for this scenario. And we review the code of these two side by side to get an idea of how languages differ, and I think we found Rust to be interestingly expressive and not that far apart from from the Python code, except that it takes longer to write and you have to think more about memory. So yeah, it's not necessarily a given that you want to use Rust. Simple things, but if you're in need of performance, I think the code does not look so different between the two versions that you would find the Python code to be superior, for instance, in readability. Okay, so let's move on now. The thing that I wanted to do next is I wanted to try and divide the work that we have in our simulation into a number of cores, so we would have threads that would process the data. So we're gonna have a look at that. I'm not again, I'm just learning Rust, so I'm not sure if we're gonna get this to work, but part of these streams are intended to be the learning curve experience, and for better or worse, we'll see how this goes. So what we'll do is we'll make a new version of our project. So we can copy our API model. We're gonna take the stream 3 version, which was from stream 3, and then we're gonna API model.stream 4, so that we have a new version for us. It was surprisingly slow, the copy operation there. I've been very pleased with Sea Lion, to be honest. I think it it performs well, or it does. It really aids the typing of the language, and of course, because of the tooling, you get a lot of nice code completion and so on that you can enjoy. Okay, so let's see. What do we have to do to make this work? So the thing that requires, there are things that make multi-threading in this project a little bit more complicated. So the thing where the actual work happens is this. Is there a way we can profile this program? Profile run API model. Okay, let me just run that. See if we can get some information about where the work happens. Cancel kernel variables. Yeah. Well, I'm not going to dig into that right now. But we can reasonably expect that most of the work happens in the next day and the infect functions. I'm going to take this count state function. I'm going to move it to the bottom here, just so that we have these two functions. We'll work on closer to one another. So let's see what happens and how the work is distributed. So the thing that we are doing is we are looping through this list of individuals. So we're looping through the list of individuals, and then we are looking for people that are infected, and so we have to look through that list of people that are infected, and then we have to pop for each of those individuals. We have to perform an operation, which is to pop find the first day of their clinical course off the array and see what that day contained. And then if that contains infect, we have to go and we have to infect people. So what would be a good multitasking strategy for this? So when we pick a random person to infect, then we need access to the population. So we cannot. So one strategy, if this was just a list of things that had to be done, if this was just a list of people that had to be processed and that required no other input than the individual, then what would happen is that we could just divide the population array into chunks, and we could give a chunk to each thread, but we could spawn, say, the same number of threads as we have processors or cores, and we would just put those chunks to those threads to process, and at the end we would join up with the updated array, and then we would be done. So that would be easy. The problem is that we cannot divide the array because we need to have write access to the array because we are calling infect on the array, although we're doing that separately down here. It could be that we could, for instance, we are collecting this new infections. What we could do is we could split this this array into individuals, into chunks, and then we could collect multiple of these lists and we could merge them up at the end. Another thing we could do is we could simply synchronize these objects with RV locks, read-write locks, or mutexes, so that we would make sure that that we just simply split this into multiple threads that are operating on the same elements. And because of the mutex or the RV lock, we would be guaranteed that we would not create a data race during the runtime. If we did that, we could get the write lock here before the new infection. So we would get the write lock here, get the write lock. And then here, before we went into person here, we would get read lock. The reason this would probably still be effective, of course, okay, so this is not so easy because we are writing. Here we take that person and we are setting that state. So we do need, this is immutable, so we need a write lock there. So for every time, the problem with the write lock is that only one thread can have the write lock at a time. So if we put a write lock here, then of course every thread will loop through their chunk of the array and not actually achieve anything. So that will not really work. But we could also say that we could get the read lock here, and then, well, if we had then asked for the write lock before we are updating the person, then we have a deadlock. We could also have one thread that took care of the infections. We could create a channel that was every time you needed to update the status or you needed to infect someone, you would have a channel that would get those things, but then you would still need a read-write lock. So yeah, it might actually not be so simple to do this in a good way. Let's think a little bit more about this. The point of an RV lock is that you can have many reads, but you can only have one write at a time. The reason we are already collecting new infections, but we could potentially also collect the new states of the individuals and then put that once we have acquired the write lock. So what that would mean is that the threads would get read locks for the data, and they would read through the arrays and figure out all those people that nothing happened. The most common event is that nothing happens to an individual, right? The course variable contains mostly days where nothing happens. So at least 75% or maybe 60% or something like that or it will be, I don't know, yeah, it will be a lone, the majority of situations nothing happens to the individuals and they can just be discarded. So if we could take all the reads and get done with that, then we could do all the writes at the end. That means that we could get the read lock here, then we could get the write lock here, and we would do this status update while we had the write lock at the end. So all the threads would loop through their chunks of the array, and then as the final thing that they did, they would then write the changes. So then they would have to require the write lock. And that makes sense, because even though you had chunked this array into for multiple people, you would have to, or for multiple threads, you still need to access the people that are in other people's chunks. So that's why you cannot just divide it like that. So what we will, I think we will try that. What we will do here is we will write another version of this that just collects the new states for these people. And then if there is a new state here, instead of setting it here, we will put it into an array that contains that, and then we'll loop through that and set those at the end. We'll see if our friend Rest allows us to do this. So we'll create a new mutable array called new states. And that will be a vector. We're going to make a tuple. I think you can just do this. So it will be a tuple of ID, and it will be a state. So now we have a thing here, and then we're going to say that for new states, we take the person. We're going to push a new one, which we have to do this, I guess, and then it will be the person.id, and it will be the last state. That work. Use of moved value. Interesting. Okay, of course. So here comes the memory management again. We have a new situation. So what we're doing here is that we take last state. Yes, okay, this is an interesting thing, because this is a non-problem. Yeah, so it says use of moved value. It's not very hard. What we're doing here is that we're taking last state that we took out of this. So we're taking that here, we're taking this value out and putting it into person. But then we are moving the last state into the person status. So once we remove this, then this is no longer a problem. ID is a copy type. So right now this should just work. Works. Oh, but it does have a crash at runtime. I don't think we will dig into this crash yet. The reason for that is that we haven't concluded what we are about to do. The most important part now is that this builds. It doesn't build. Oh, of course I'm pushing the debug button. That's fine. It builds. Let's actually get rid of some of these. We have some errors here. These are not errors; they are warnings. So we will get rid of them. See, because it doesn't look good in the output. So let's build it now. This is private type simulation state in public interface. Yep. So that probably means that we are. It should be public. Sorry, short digression here. We'll put all of these to be public. That basically means what gets exported from this module. Unused result. We will just do unwrap here. Result means that sometimes you get error handling or success or non-success. So for instance, at the end here, we write a CSV file with the data, and then we did not do error handling, and that's why we got that error message right there. Okay. Let's get back into it. Now the build output is cleaner. Okay, so we're still doing our next day thing here, and we are we have now said that we are also capturing these states here for people. So the people have new states, and then at the very end we have to loop through those new states as well. So we're going to do for state. For new state, or this is a change. So for change in new states. So and then we do indeed get the ID and the new states. Then we say we gotta get the person. So we'll do let we get that person mutable person equals self people get mute. Actually, we don't need to put mute here, I think, when we do this. So that was something I discovered. That's a faulty way to think of it. And then we take the change dot Why do I get something out of a tuple? Like this. Cool. Okay, so right now we see that this is an option, which means it could or could not be there, but we'll simply unwrap. Yeah, so now we get a mutable person, and we then go person dot status equals change dot 0. So you can't do like second or no. No, we're gonna do 1. Okay, so now in principle this should do the same as the code we had up here, right? It's just that it does this afterwards. Okay, so we run a simulation of 100,000 people. Okay. Interestingly, look at that. That seemed to take a little bit longer. So we were talking a moment ago about how this completed in 0.2 seconds. Let's see now. So what we did now is we actually, let's clear this console. So we went into epi model, stream 4. So right now we built this using the using non-optimized mode because we're debugging it. But if what happens if we go into what happens if we cargo build release? So we build a release version with the optimizations, and then we're just going to see, we're going to time that one because it will be actually very interesting. Let's just let that build, and then we go to the new one at the model.stream 4, and then we have a look at the output. So the output is in target, and then you have debug and release. We go into release. We are doing more steps, right? So now time./epi model. Just going to see that the build completed. It did, finished. Still very fast. It's definitely not slower than before. I'm doing it again. Interestingly, it seems like it might actually be a little bit faster than the one we had before with this change. I don't know why that would be. Maybe the compiler found some way to optimize it. So this feeling here that it was slower is not the case. This version is not slower. So what we are doing now is, of course, we're still borrowing. We're getting a mutable iterator here, but we are not. But we no longer need this iterator to be mutable, and because we're going to require a read lock here, then it cannot be mutable, right? So we can try this. We can try to get the iterator as non-mutable. I think maybe we have to change this too. Let's see. Cannot borrow as mutable as it is behind the and reference. Okay, can I simply do this? Okay. Let's see what we are doing here. I'm just going to try this. This is working. Okay, so what are we doing? Okay, so we are still doing the same. We're doing the same thing. We're not. Of course. We are mutating the person because we are. Yeah. We are mutating the person because we are removing from the index of that individual. We are removing one element from the clinical course. So we are removing, we're not getting the object at index 0. This is not going to be pretty, but I think we can then just do get. So if we didn't now remove this item, nothing would change in the simulation, and that's wrong. So when we are also modifying the person down here, we will get the clinical course and we will remove element 0. Now we have moved all the write operations that we have down here. We have changed. So these are now the person write operations. And so what we are changed now is that up here we're just simply inspecting the current day, and then we are making some decisions. Okay, more problems. So we are now taking the last state out of the current day, and then we are. Okay, so is the problem here that it's not a copy type? Can we clone it? No, we cannot clone it without it being a copy type. I wonder if the reason, yeah, I think the reason this is not working is that we cannot simply take this, we cannot copy this value. Right now we are moving that we are not allowed to. Let's see actually the error message. Mismatch types. Okay. Okay, so of course we have changed something here. What have we changed? The person. So now all of these are borrowed values. That's our problem. Okay, that is a little bit interesting. Yes, that's not going to fix it either. So what happened here is that now all of these are references, and now we are getting a reference to this ID. But what we do want, we want to clone it, but we can't clone this. I think that should work. Yeah. The last state we cannot clone, I think, because it doesn't have that trait. No. The thing that's happening here is we are trying to move, or we're trying to so we can just clone this, but I now want last state to be I want it to be able to take this state and put that into this other list of new states. So what I think we can do is we can take state and we can make it clonable. So how do we do that? We can derive, and then I think it's clone, copy clone. Is that gonna work? Still mismatch types, but I think we can now do clone. Okay, it runs. So what I think we're making a copy of that state, and we will change the person. So we're moving that into this array, and then here when we are doing the remove, when we are doing it here, when we are looping through this, we're taking that value out again. Is that not what we're doing? Let's one more time try to build this with optimizations and see if we have altered the. It's faster. Significantly faster. We went from 0.2 second to 0.1 second by cloning the value. Whoa. I'm not sure I'm going to pretend that I fully understand why this is faster. Does it mean that because we're now doing everything in here, is it something to do with not passing these things as references anymore? Is it so that copy types are faster? We should probably also have a look in the output file to see if it still sort of does what we think it does. A worst case scenario. This is funny, LibreOffice makes itself tiny. A worst case, look at that. So now nothing changes in our simulation. So we have not optimized the situation. We have, the reason it's faster is because nothing changes in our simulation. So it's not actually faster. It's not just not doing anything. So what are we doing wrong? So, okay, this is intriguing. So we are looping through, and we are looping through 10 individuals. We can see if we, just interestingly, we'll see if we ever get here. So is the problem that we are, so actually what I'm going to do to prevent this problem from happening and prevent us not being able to spot this problem is that instead of writing the results to CSV, we're going to print the output table. So we're going to do sim output dot print, I think. When we run the simulation now, we will get this, or we should get this table here. Yeah. Now we can see that even we can actually reduce the amount of people in the simulation a lot, so that we can see if anything actually changes. We're seeing that nothing changes. The final day, here 300 days, have exactly the same amount of people being sick and so on as beginning. So we have broken our simulation instead of making it multi-threaded. What did we change to make this occur? Why is that happening? It seems like people are no longer being... It seems like people are no longer getting infected. Okay, so that probably means that we never get to this. Debug it. Wait, no, that breakpoint is never fired. Is there ever a state change? Did it stop there? No. No, so there's never a state change. Can I stop it there and have and inspect this variable? Yep. So new states. New states appear to be empty and new infections appear to be empty. Okay, so let's try this again. Does this mean that we never get in here? No. No, we do. We have, in this case, we have a person. So you can step it one forward. Did that work? Try one more time. Are we there now? Is that it? Yeah, let's try this one more time. It seems we cannot put a breakpoint on that. Okay, so what are we... Okay, so the person, we have a person here, and that person should now be infected. So we can have a look in that object. Yeah, so status is infected. So the person is indeed infected. And the clinical course of the person, let's see if that's developed. It is. It is an array of sick days. And the final day is has state recovered, and it is a conclusion. And we should also still have on the third day it infects, on the second day nothing happens. Yeah, so that is correct. So what happens next here is that we match this. So this has to... Is the problem the clone? So let's go here. At some point it should infect, so we should get to this point, right? Try and debug it again and try to see if we ever get to either conclusion or new infections. No, we don't. Does it seem unable to get this? Let's add a little print line here. Actually, let's do let x equals 5. Let's see if we can debug this point, because I want to see what happens in current day. Maybe this one gets optimized out. No, there you go. Okay, current day. The current day is a sick day, and it's none, so nothing happens. Oh, of course. Of course, it makes sense. So the problem here is that, in fact, we don't want this this removal here. We want that to happen. We want the removal from the index to happen to every individual that we picked out. So we have, yeah. So again, we have the problem that we need for every individual in this list. We need to read and write. I feel like what we're doing now is, because it's both a read and write situation, we have to loop through the list one more time, and this does not seem to be optimizing at all. It seems to be de-optimizing it. Because if we wanted to do this, we would now have to get this. We now have to get this iterator one more time, once in read, where we did all this, and then we would have to get it. We have that. Yeah, this is our problem, right? Every infected individual needs to have a change take place. So this is simply not going to work, because we need to pop one element off every sick person's we need to pop one element off every sick person's clinical course. And that has to be the first item. So we need that person to be mutable to progress the simulation. So we cannot very, very easily divide these two things. Okay, so we are still having trouble. Because if we wanted to... The question is if this sort of architecture that we have here supports this multitasking in a good way or not, or whether there are other ways we could solve this problem. I think we need to think a little bit about this one. The one obvious thing we could do is that we could simply say that we don't need to. This comes back to one of the things we've been working on in previous streams, is this idea that you may want to you may want to have some information. The only reason we need to, or no, it is not true. Actually, every single thread has to mutate this vector. Hello, Tale of Legend. Sorry, you caught us in a moment here where we are a little bit stuck on the multi-threading. We're trying to optimize this. We're trying to make this structure multi-threaded, but it's not so easy to figure out the best sort of architecture for this one large array that has to be manipulated. So this would, we could of course simply ask for a, we could ask for RV lock on the entire thing. Then we're sort of looking at the mutex anyway, and then if only one thread can have access to this array at a time, we're not really getting any benefits. And because we cannot separate the read and the write operations very, very easily, then we are still struggling with the same problem. This might be that this is not a very easy structure to optimize. The one thing we could potentially do in this simulation is we could find a way so that we didn't need to pop the element off of the sick day, the clinical course array. That could potentially work. In that case, we would have to say something like we're looking at, instead of modifying that vector, we are generating it when a person gets infected, and then we are picking and then we're looking at the specific index in that vector, and we can read that unmutably. The problem with that is, of course, then we're not solving the problem in the sense that we would like to have this structure as we have it. So we're modifying the structure to be able to work this way. But yeah, this one is a bit tricky. On the other hand, it might actually be that the rest here is trying to save us from shooting ourselves in the foot. Because if in Python, for instance, we would probably be able to do all these things unhindered. So we would be able to mutate these individuals. We could also have a lock on each individual. So, well, how does that work memory-wise? Could we add each individual would be behind an RV lock? We wouldn't have to lock the entire. That's of course a thing, because the threads work on the individuals. The question now becomes, can we have an RV lock on the individual? If we're gonna divide this thread into this feels messy, right? It feels really messy. Because one thing we could do is for each individual, we could generate the clinical course up front. And then we could say that, okay, this I think would be a solution. So whenever we generate individuals, we also generate their clinical course. In fact, their clinical course is exactly the same for all the individuals in this particular simulation. So if we did that, then we would not really have to mutate these individuals unless when we change their state. So it means that this thing that we are doing here, where we are removing one day of the sick days on the clinical course, we're removing one element, that would no longer be necessary. And then the state change would only happen when you knew that in fact, we could say that the state change would be a function of the day that the simulation is in. So then the person would be recovered after a certain day. So that would make that entire thing would then be just reads. So then we have removed, in some ways perhaps this is a more elegant way to do it as well. We would simply remove the need to modify the object to say if the object is beyond, or if the object is, if the person is sick or not. Potentially, should we rewrite the simulation to do that? It feels like there's two sides to this. On one hand, we are now rewriting the data structure to fit the memory model and the multitasking paradigms, and perhaps that is good. The paradigms are there to protect us from making mistakes, and the idea is, of course, you would have this fearless concurrency. So if we made this change now to the person object, then we would be able to we would feel safer that everything worked because it would just work within the model that we are in. So perhaps that is not a bad idea. Perhaps in that sense, it makes more sense to modify the model to work in a safe way than to shoehorn this shoehorn this initial approach into the memory model by creating all kinds of cells and things like that, or using these runtime APIs in Rust that doesn't have the same memory management. Yeah, so maybe that is something we should try. Maybe we should rewrite this. So it would mean that the state of an individual, okay, so we would rewrite the person object. So what happens is that when a person gets infected, well, then we have to mutate the individual because we don't know when that happens. But we would say that the person would carry a number that is the day that the person gets infected. And then the day that the person gets infected, the person becomes infected for a certain time, and then the last day is another number. And whether the person is recovered or susceptible depends on that number. So in this case, we have rewritten the simulation so that we don't need that vector of sick days, or we could have the vector of sick days, but you would only have to look at it when the person's state was. You'd only have to look at it during the period when the individual was sick, and you would never have to mutate it again. I think this would work. Makes sense. It also allows us to do one more thing, and that is it allows us to try to unit test this individual, because this is a complex mechanism we now have on the person object. Okay, that should work, right? So then, as you loop through the situation, the individual only needs the person. The only thing we need to know is we need to know the day of the simulation, and when we know the day of the simulation, we know if the person is sick or not. And then we don't need to pop anything out of that array that contains the sick days, so we don't need the person to be mutable while we are observing it. Then that means that all the threads can have the read lock and work on the list of people, and then they will only need a write lock at the very end when they have concluded their inspection of all the people to see if they need to have a state change. And in fact, the only state change we then have to do is the infect state change. So that's the only write we would have to do. So we are simplifying the model quite dramatically, and it will not make it less readable, I think. I think this will still be a readable construction. Perhaps it requires much less manipulation, at least, of memory. So let's do that. And in order to do that, I think we'll start by moving the person object into a separate model. Because now we're going to add a lot of functionality to person, so it becomes more like a class. So I think we'll do that. So also again, hello to Taleb. Thank you for saying hello. Are you into Rust? Are you just learning it? Are you an expert? Or did you perhaps expect a game? As many people here do, I hear. Let me know. Okay, so we're going to create a new Rust file, and that's going to be a person. So we're now going to move our person object into that one. I think we're going to keep these things up here because we might want to use that later. So person, we're going to move that into this one. So now we have put the person in their separate file. We will attach the person module to simulation. So we'll do mod person. If I understand this correctly now, okay, mod file. Why can't you find person? Do we not save it? What happens if I try to create it? Okay, so that doesn't work. Why does the D? Okay, so scary. So we cannot use person. Because why can't we just import this module now? Does the module have to be from the main? That I can't believe that. Okay, so that's weird. In simulation, can I now use the person objects? That's what I want to do. I want to use person. Person. No, I cannot. Or can I? Does this build? No, unresolved import person in simulation. So why is that? Yeah, maybe it doesn't include anything. No, it's public structure person. So in simulation, we want to use mod person. That is intriguing. Why does it not allow us to do that? That's really surprising, because I would expect this to be a chain of imports, right? So that should work. We can also do create person. No, I can't. What happens if I check create module? Ah, look at that. So it now expects there to be a okay, did that work? So if I go back to simulation now, yeah, now it imports it. Okay, why is that? This surprises me greatly. So I would expect that simulation could import a file that was next to it, but now we have created inside simulation a person object. I don't think we want that. I would expect the behavior to be so that this would just work if it was a, can I do relative paths? No. I guess we have to look that up in the Rust docs, because that is a surprise to me. So let's look at that. Rust module, Rust mod, relative. I have actually encountered this problem before, but I can no longer remember its conclusion. Okay, we can actually put a path thing here, but that doesn't seem nice. It does not seem like the way you would want to do this. We can try it, but let's see, path, and the mod is person. The mod is person. So now it allowed me to do that. and it allows me to import person, and now it should build. Nope, can't find EID. Yeah, of course, that is in the person scope. Yeah, so all these things are from simulation. Mod simulation. That is, of course, also not allowed to do. We'll do the same thing again, although I think this is probably not good. The way what we're doing here now. Are we allowed even to do this? So this will import some. We're now making a cyclic import. Circular modules, yeah. So that didn't work. So I actually don't think circular modules are always bad, but I'm just a little bit surprised that this became a problem. To be honest, I think we'll not fight this animal right now. We will take this. And part of that is simply because this is a stream and we want to have some progression. So we will take, because I think this might not be as easy. So we'll take the simulation and we'll put the person back in. Down here. We'll remove this person file for now. Okay, so we are using person anymore. We'll remove it from here. We no longer want the person import, so we'll remove it from here. Definitely move that one. Import. That's okay. Okay, so it runs again. Yeah, so the thing we wanted to do was that we wanted to change. We'll say what is the. We'll add some new fields. The first is day infected. And that will be, it will be, what are our days? Our days are I32s, I think. And then we'll say day. No, we'll do that. Okay, so we will remove the status. And the reason for that is that the status is now a dynamic property. In fact, let's add the implementation right here. So we will do implement person, and then we'll have a new function, which is a public function. Okay, so that doesn't have to go there. There'll be a get status. It will take a non-mutable reference to self, and it will return a state. And because the status is now a copy type, we can move it out rather than borrow it. So, in fact, we'll do this a bit in a more Rust way. So, day infected will be an option of an I32, and because it might not be that you are infected, right? So here's what we're gonna do. We're gonna match when we get asked. We'll match self.day infected. And we're going to use cline here, and oops, we're going to do fill match arms. So either you get a day. If you are none, then you immediately here you return state susceptible. However, if you are some, yeah. So there's a lot of like syntax highlighting here. If you are, yes, if you have a day, then we have to say that, okay, so what happens is either you are between the day that you got infected and you are, actually what we're asking for is we ask for a status on day. Status on day. Now we're saying that we have a day, and then if you have an infected day, okay, so if the So if the day is less than or equal to infected day, then we return state infected. In fact, we will return the state, and we will return an option of a sick day. Okay, so if the current day is bigger or equal than infected day, then what we want to do is and day plus the self.length of or the self clinical course length. So we have the length of the clinical course. If that is bigger than the infected day, than the current day, then what we do is we return that element from the sick day. So we will ask for that. We will have to actually clone that out. So we'll say okay, so if the current day is bigger than or equal to the day infected, so that's the first condition. Actually, we're going to do we can do two nested ifs here. So this is you are in or beyond the infected period. Then if the day is smaller than or equal to the last day of your infection, which is the infected day plus the length of self clinical course length. If the day is smaller than that, then you have a sick day. Then you return. In this case, the state is infected. So actually, we're going to do status state. So then you are infected, and you return some, and you return the self clinical course get. And then we get the sick day. Yeah, actually, it gets really messy, right? So we're gonna then, if this is the case, then we have sick days. We're gonna do sick day equals self clinical course get, and the index will then be sick day idx. Let sick day idx equals, and that will be day minus this. No, it will be that minus day, right? It will be that minus day. We will get the sick day IDX, and we will unwrap that. Oh, it's starting out a bit messy, isn't it? This is gonna not look very pretty. Okay, so we have then like a course, yeah. Then we get the sick day and we unwrap that. So why is this now an unknown? Because we know that this is a vector of sick days, right? So we're asking for a sick day index, and then I'm really a little bit surprised that this is that. And then we are also returning some sick day. So that is the sick day. So this it surprises me that we cannot say this. This is an option of a sick day. Found unknown. So why is that not compiling for us? Let's have a look at that one more time. Yeah, so we have the sick day index, so we can get that. And we do that by looking at the final day of the sick day, and then we subtract the day that we are given. So that's fine. We know that clinical course is a vector of sick days. So why can we not get that? Do we have to like borrow it or something? No. If we remove this, what do we get? We get an option of something, but it doesn't. I don't fully understand why it cannot figure out what this is, because we do know that the clinical course is a vector of sick days. So we actually want that to be a sick day. It can also be a borrowed sick day. That is fine, and it is. And then we will clone this, and because we need to clone it, then we will make this type a copy type. We're allowed to do that. Okay, so more trouble. Yeah, so in the event that in the event up here that there are that we are not infected, then there is no sick day. In the event that we are infected, then the status. So we are yeah, so that's good. Then the last scenario is that we are done with the infection, and then we return a state recovered, and there is no sick day. Okay, so it's still not allowing us to do this. We can just add a clarification here. So if we are in the sick day period, are we in the clinical course period? That's what we're trying to figure out here. Because if we are, why does this not allow me to do that? Yeah, so it says the size is use size, so we have to convert this to I32, which should be fine. And then I guess this is the same. So it's because these things are done twice, we'll say let last sick day equals, and that is the day that we are infected plus the duration of the condition. Last sick day, and then we can say, okay, so if the infected day okay, so let's see, last sick day there, yeah. So okay, so we are now looking, are we in that period? So we say if is the day smaller than or equal to last sick day, then we are there. And the index of that sick day will be the last sick day minus the day. Okay, what happened there now? Yeah, so the index is the last sick day minus the day. So why did that cause trouble? Is it a syntax thing maybe? Oh, fascinating. Why is this trouble? Is it because we're somehow changing this now, or? Actually, I think we need to cast this into a use size to get it as use size. No. Is it because we're not returning something down here? This must be a syntax error of some kind. If missing an else. No, so it's closing it there, it's there. It's the sum. Possible that when we get here, it has to be. We have to provide a default. Oh yeah, of course, this thing. Maybe that is simply it. functions return, a function returns that instead. Okay. I thought that we could return out of here. Is that okay? Can we simply do this? We can say return. Then we don't need this, right? So this, the last statements inside here, I guess, would be So what happens here? I think now it works. And so what happens is that the last, okay, this got really messy, didn't it? Okay, let's walk through this one more time just to make sure that this works. So we're given a day of the simulation, then we match at ourselves to see the infected. And if we are not infected, then we are both susceptible and we don't return a sick day. If we are infected, then this infected day is passed into disclosure. So we have we are infected. If the current day is bigger than or equal to the infected day, then we are infected. Then we need to deal with that. Okay, so then we calculate the last sick day, which is the day that we got infected, plus the length of the clinical course. Then if the day, okay, so we have calculated that. If the current day is less than or equal to the last sick day, then we get the index of the current sick day in the clinical course by taking the last sick day minus the current day. If the last sick day is day 180 and current day is 178, then this becomes 2. So we will then have, yeah, of course, it starts at the other end, so it will be the infected day plus last sick day minus the day, because it goes from the beginning, right? So then we have no, actually it's much simpler. It will be the day minus the infected day. Because if we are at day 180 and we got infected on day 170, then it will be 180 minus 170 and we are on sick day 10. So that should be correct. So the sick day index, yeah, that has to be it. Then we ask for the sick day. We get that from the clinical course. And then we return the status of infected because we are currently in the infected period. And then we return a clone of the sick day. We don't want to borrow that. We just want basically the information in that object. So we are passing that out. And then we are, in this case, we are no longer, our day is beyond the last sick day, and then we are recovered and we have no sick day. Does it build? Well, I actually don't expect it to build. Okay, a lot of problems here, if maybe missing an else. Oh, we have to have else. Thing is, of course, yeah, of course, in this case though, we are the else is redundant, isn't it? Because we know that if we have an infected day, then our day will be beyond the infected day or equal to it. So I am actually running out of time for this stream, so shortly I will need to drop this, and then in that case I will continue this and try to make this optimization later to try and see how that works. But because this now we're just into the logic stuff here. Just going to make one more stab at this. So we know that if we have an infected day, then the current day must be higher than the infected day. So we actually don't need this clause at all. the condition will never happen because you do get infected. When you are infected, you get infected on the day that you get infected. So this part is redundant. You are now infected, and your infected day will always be bigger than the current day. So we can safely remove this if else. It will not provide us with any problems. The other thing that we have to do now is we have to change what happens in the simulation when you get infected. Actually, there's a lot of things we have to change. But on the infected, what happens is that you no longer change the state of the person. So you will get the person and you will see if that person is susceptible. So the way you will do that now is you will do match get person dot get status on day, and infect will now need to know the day. So we will do day. That is a I32. That means that now when we are infecting, which we do in the next day function, we are going to put, let's see, when we infect a person, we need to put the current day. Current day here is U32. That does definitely not have to be U32 because we can never have negative days. So that's fine. So we are now saying get status on day, and then what we are getting back, of course, is a tuple. So what are we matching? Well, we're matching the first, which is the state. Okay, so if the person is susceptible, then we continue. If the person is not, then we return, because we're not doing anything to anyone that's not infected. Then we generate a course, because now we are infecting the individual. We generate a course, and that should be fine. And then we get the person as mutable because we have to change the person. And what we're going to do now is the person dot day infected is now the day. Okay, so day is I32 and for an option of I30. Yeah, so actually, so now day infected is some, and it is day. We could consider putting this on the person object actually, but that might also open a can of worms, as we have seen before. So the person's status is no longer updated, but the person's clinical course is set. So that should work. Then we need to do more things. So in this case, we're counting state. So this is just to sum up things. Then we need to say that the person's status is, yeah, actually, so now things get very, we have to pass the day now into a lot of these functions. So we can now get it on day 32. So that means that the p dot get status on day. So that should work now. Okay, and then so count state, we also need to now pass them on the day. One interesting consequence of this is that we can, as the simulation has run, we can actually go back and collect all this information, because we no longer need to do this on the fly while we are simulating. So that is an interesting change in how this would work. Okay, so what more do we need? This works the same way. Yeah, so when a person is sort of created in the system, we no longer need to set the status, but we do need to change the day infected, and the day infected is none because the person is not initially infected. Okay, so what did we do? We changed to say that the status of the individual is dynamic, and we only need to mutate the person. We no longer, so what the consequence of this, if it worked, was that we no longer need to take, so now we no longer need to take this current status out. Okay, so let's think a little bit more about this now. So we have changed the way this works. So we are getting the people and we're getting them as non-mutable. We're finding the ones where the person dot get status on the day, and we need to take the day, and where that status is, actually we can put this on a new line to make it a little bit cleaner. This iterator construction is getting quite nasty. So we're getting an iterator of people, and then we are saying that we want them with the status on the current day to be infected, and those are the ones we are going to change. Then we need to do we need to get the sick day? Yeah, so we get the current sick day. So what we do is, of course, the thing we're filtering on here is the thing that we want. So that is not very nice. Now we could see if we could improve that. So the problem is that our current day, we know that the person is now infected, right? Yeah, there's probably a way to optimize this. So we will get the person, and we'll get person.get status on day, and we'll get today. And we want the sick day, and we will take and unwrap that because we now expect that to be the case. So we do have a sick day here. And of course it returns a cloned value, so I think this should be actually fine. So now we have the sick day, and then we can see what happens. If nothing happened today, then because now it looks into the array of the clinical progression, and it will pick out the sick day. If nothing happens today, then nothing happens. If the person infects someone else, then we push that onto the new infections array. And if the conclusion is today, actually we no longer need this. We no longer need the conclusion part. The reason we no longer need the conclusion part is because everyone concludes at the end. However, we might want to keep it for the future. Yeah, so we no longer need this new states. We can remove that. The reason we may want to keep the conclusion is that in the future we may want to change the simulation so that some people will pass away. But for now we will just keep that everyone recovers. And that is actually what happens in this status. Let's see the status on day, right? If you are beyond the last sick day, then you are recovered and you don't have any sick days. Okay, so now we're left with a new infections array, and if this, it probably will not compile. It does not compile. This function takes 2 arguments, and that is a deceptively easy thing to fix. Yeah, so initially on day 0 or day 1, yeah, it starts on day 0. And the same happens when you infect the individual a little bit later. Let's continue building it. Cannot be indexed by, yeah. So in this case, what do? Get status on day, we say, yeah, so that has to be as a use size. Binary operation cannot be applied to type simulation date. Okay, so do we need to, let's see where that is. Yeah, so of course we are also looking at the state, which is the 0. Because we're returning a tuple, this is probably the same type of problem. So remember that now from the get status on day, we're returning a tuple, and the first argument is the state, and the second is the option of sick day, if you are sick that day. It compiles. And now thinking about it, it gets, probably the syntax of this is much dirtier than the syntax that we were looking at in Python in the beginning of the stream when we compared the performance characteristics of these two. Let's build. Okay, so we have 4 warnings of these things. Field is never used, ID. We can probably remove that now. I agree, because we're not actually storing the ID of the individual, but at some points we have kept that variable. So we will just tidy that up. Import, that's okay, we can remove that. It's nice to get these warnings out of the way, unused. Yeah, actually I will keep that because we probably want to write the output again. Last state, yeah, so we do that because we're no longer using it. Okay, run it. Oops, and we have a panic. So it panicked at. Does it stop on the point? No, it doesn't. It crashes here. Let's have a look and see what happens there. Practically. Move this. Okay, so we are asking for the sick day. Okay, so if the current day is less than or equal to the last sick day, then we ask for this index, and then we ask to get this out. But this should not be a problem. I think maybe what's happening here is that we are misaligning the array. Yeah, we did. Okay, so something did happen in our simulation now. We did have an increase in sick people. Yeah, so I think actually now it ran, didn't it? Let's get our number back up and let's see if the output of the simulation is as we expected it to be. So in main, we will now simulate, and I guess we were looking at 100,000 people before. Let's just run it first. Felt slower. If you just look at the table, yeah, the outputs look correct. So this column is the number of infected, this is susceptible, and this is recovered people. We see that the infected people dramatically rise, get high, and then that gets low, and then a certain amount of people, roughly 6%, never gets the disease because they are accidentally they are never picked, and by the time they could be picked, too many people are immune for them to be found in the population. That works. Okay, so now, principally, we should be able to multi-thread this. We have changed quite a lot, though. We have removed a lot of vector operations. Because before we were popping people out of a vector, so we were reallocating that vector all the time. We were changing where it started. So now it will be super interesting to see the performance characteristics of this. Okay, so let's build it for release. So we'll do the same optimizations as we did before, and now we'll time it again. It performs, actually now it did print this enormous things. That is probably not good. So what we'll do is we'll remove this print line and we'll let it do the same output writing as it did before. Because otherwise those could be variables in what we are doing. Especially when the times are this short, let's say. But they were not. Okay, so with these changes, the operation takes roughly the same amount of time. That tells me, first of all, that these vector operations that we were working on were they had surprisingly little impact on the performance. So it seems that you could do quite a lot of manipulations of vectors in real time without losing the performance of this system. Okay, let's go back, and now we can actually try to multi-thread this. And that'll be the last thing that I'll do today. This was a long time coming. So what we wanted to do is we wanted to spawn, okay, so on the day when we do the next day operation, when we do this thing here, so what does next day do? Well, it creates a list of new people that are going to be infected. Then it loops through the individuals. It picks out the ones that are going to be infected, and then at the very, very end we go through that list and we create and we infect the new people. So the whole reason we changed this thing up here to be a dynamic effect of the day was that we can get a read lock here, and then we can get a write lock here. And when we do that, we end up in a situation where we can have multiple threads operating on the next day procedure and before they end up here, and then we can have an RV lock, and we can make this entire simulation thread safe. Last thing I'm going to do is I'm going to, before we get into the multitasking, see what happens if we remove this this reporting. Because now if you're going to make this multi-threaded, we cannot have the threads perform this reporting in this way. We have to sum it up afterwards. In fact, what we'll do is we will take this part out, this part that does the, it probably goes somewhere else as well, naturally. So we will create a public function called update stats. That will be, it will take an immutable self. Actually, it has to take immutable self. There you go. Yeah, so it nothing had changed there. We can just actually we can run it now. We can just, before we split, we can do self dot output. No, it's called self dot update stats. And now this should run just as well. No, it didn't. I cannot find when day. Yeah, update stats for day. Yeah, so it has to be given the day. Oh, I type something. To be given the day. We're now going to say that that takes day, which is I32. Yep, that compiles and runs. Okay, so the next challenge that we have is that we want to split this into 10 threads, and we want, or let's say, okay, let's split it into an arbitrary number of threads. We're going to do let n num threads or n threads. We're just going to hard code this for now. So we want to split it into, let's say, 4 threads. So I'm in a virtual machine. How many threads do we have on this thing? Or how many cores do we have on this? So we have 8 cores. So let's divide that into 8. So what we need to do now is we need to split this person array into multiple chunks. So I think actually there's a function to do that. Otherwise we will have to find another way to do it. But it would be nice to separate this actual performance out into a separate, or this what actually operates on the array here into a new thread. But for now, because I'm a little bit short on time, so I'm just gonna keep it in one function for now. We're gonna see if we can make this thing where you have multiple chunks. So let's say self people, and then you could ask for chunks. Does it be mutable? It doesn't. Actually, look at this. We actually have a choose here as well. Let's see how the chunks thing work. So we're gonna do rest vector chunk. Yeah, so it divides the vector into yes, yeah, so this is what we want. We want multiple of these. Yeah, we want to divide it, and we want to have a rough estimate. So we will take, so what we'll take is we'll calculate the chunk size first. So we will let chunk size equals, and that will be the length. So it's the yeah, so it's the self people length. We divide that by n threads. This will give us a, okay, apparently it gives us a U size. I wanted to floor that. Can I do as f32? And it says as f32. Then I can floor. And we convert that back into U size. Oh, that looks dirty. Is that a good way to do it? I don't know. Let's get the chunks anyway. Let's get chunk equals. So we can actually try this being single-threaded initially. So we can take, now we take self.people.chunks, and the chunk size is given here, so we have that. Okay, so now we have a chunk array of person. Nothing happens with this one. Can we run it? Yeah, so it runs. Just to speed things up a bit, we're going to remove a lot of people from the simulation. So we will now only simulate 10,000 people. But then it's fast. We'll just run it fast. So what we want to do is we want to spawn a new thread for each chunk, right? But we can also do this sequentially. So we're going to do for chunk in chunks. And then we will, until we update the stats, we want this to run inside its own, we want the update function to run inside its own thread. Okay, so principally if I build this now, it should, no, cannot borrow self as mutable monoids. Yeah, so maybe it's now we are borrowing something up here, but what we want is we want this chunk, and instead of self people, we will now iterate over the chunk. Fingers crossed. No, cannot borrow self as mutable because it's already borrowed. Okay, so what is our problem? Okay, so we do an immutable borrow up here. So that's when we chunk it. Then we mutable borrow later, and then we do mutable borrow here in self infect. Yeah, so that is actually we're gonna. The idea here is, of course, we were going to resolve this. We're going to resolve this by making it's possible to get the RV lock. So yeah, so that I think we can still do this, because what we're going to do now is we're going to put the person vector inside an arc so that we can have multiple references to it, and then we're going to put the person vector inside an RV lock, and then we're going to put that inside an arc. So we will yeah, we will have it like this. Let's see. Yep. We can just see that this compiles now, just for that. That does compile. But it's really hard to test, right? Because we cannot actually, right now nothing changes in our simulation, and the reason is that we're not actually we're not actually doing any infections, so nothing really changes apart from these infected people getting recovered. So because it's getting quite late, I think I'm gonna take a quick break in this stream, and then we will continue from here a bit later today in a part 2 to see how this goes. But the plan going forward is that right now we'll change this, the people array, we'll put that inside an RV lock. And then, and the reason for that is that we eventually want to have this in multiple threads. Then we'll put that RV lock into an arc, which is an asynchronous ref cell, asynchronous reference counter, and then we'll pass the reference to the RV lock to each thread. We'll spawn a new thread for each chunk that will take care of this, and then we should be allowed to do infect. Yeah, so I think this will be it for now. I'll be back in I guess an hour or something like that, and then I will continue the stream and we'll try to get this run. Okay, so thank you to anyone watching, and sorry for the slow progression here, but it's again part of the learning curve. And of course, we did have to restructure and refactor our program for this approach to work. If anyone has any suggestions for how the task that we try to do now could be done differently, then feel free to make a comment, either in the comments here, or if you're watching this on YouTube later, you can put a comment below. Okay, thank you very much. I'll be back shortly with more learning curve and troubleshooting and all that. Okay, cheers.